Alright, well we're going to learn a bit about Hubble's law by doing a lab activity. And I just want to introduce this lab activity by going through basically the first page or two of the lab with you, just kind of talking through how we're actually going to do this lab. You'll read through those instructions, but hopefully they'll make more sense after you've watched this little video. First, let me just remind you about Hubble's law and talk about what we actually can figure out from this really cool relationship that Edwin Hubble discovered. So as you saw in the video, Edwin Hubble graphed velocity of these galaxies, which you could measure from their spectra, and we'll see how that works in detail in just a minute. And he measured that against the distance to these galaxies. So you think about any mathematical relationship as relating variables together. If you know any one or two of those variables, you can figure out the value of a third. And I just want to illustrate that with you here a second. So Hubble found this relationship, the linear relationship between velocity and distance. Now I just want to think about what this relationship is telling us, which is really cool. And I want to illustrate this by talking about the units of these things, right? Everything we measure has units to it. So velocity generally we'd say has units of meters per second, and distance generally would have units of meters. What I want us to think about in particular is what would the slope of this line represent. And maybe you've already heard of this or seen it earlier, but the slope of this is particularly important of this relationship that these galaxies fall on, right? So galaxies all lie along here and make this linear relationship. The slope here is always given by the rise over the run, right, in any mathematical relationship. So the rise being the vertical, the run being horizontal. So let's just look at what these units would represent. The rise would be meters per second. The run would be in meters, right? And this meters would cancel out. And so just look at what units we'd have left here. The slope, whatever that number is measured in, the units are 1 over seconds. Now the slope we usually refer to as Hubble's constant. And what's striking is that the units of Hubble's constant is 1 over seconds. And now, without any form of proof, I'm just going to tell you what's striking is that 1 over Hubble's constant, if you were to take 1 over Hubble's constant, you get a number that is measured in units of time, like seconds. And so whenever we're looking at these like big picture things, right, and we're looking at how galaxies are moving in the whole universe, what this is telling us here is that 1 over this Hubble constant is a time measurement, which is actually an indicator of the age of the universe. Right, the age of the universe. That's making some assumptions, like that the expansion of the universe has always been happening at a constant speed. Nonetheless, this is a really interesting measure, particularly as we try to understand how long has this universe been around. It's pretty cool. This is what we're getting at in the lab. Our goal is to use real pictures of real galaxies and to use that to measure the age of the universe. It's really cool. So this lab, we're going to literally measure the age of the universe. I think that's really awesome. Now we've got to talk about how we're actually going to do that. So to measure the age of the universe, we have to do two things for a variety of galaxies. We have to measure the velocity of that galaxy, how fast it's moving toward or away from us, and we have to measure the distance to that galaxy. There's cool ways that we can do both of these, but they take a little bit of an explanation. Let's start with the issue of distance. Measuring distance is tricky to do. We've talked about parallax and all sorts of different techniques that can be used. A common technique that's used is the standard candle, right? Where if there's something kind of like a candle, although it's usually a star or something else, that is a known brightness, right? If you know how bright that candle is, and then you know how bright it looks to your eye, here's my eye looking at it, okay, then I can figure out how far away it is because I know that light follows this inverse square law. Right? The brightness of an object falls off as the square of distance. So if I know how bright the object really is, and I know how bright it appears to be, I can figure out how far away it is. This is a standard candle. What we're going to have to do in this case, we can't quite use a standard candle, although you can. That's what Hubble did. He found Cepheid variables, which are standard candles. We're going to use a standard ruler. So the idea is very similar, except instead of a known brightness, you have something that is a known size, kind of like a ruler out in space. And if you know how big it really is, right, which we usually refer to as a capital D, if you think back to our small angle formula, we know how big it really is, and we know how big it appears to be, which we usually express with an angle theta, or maybe alpha. Okay, we know how big it appears to be in our sky, an angular size. Then we can figure out the distance to that object using the small angle formula. Now, in the case of galaxies, this is what we're going to do in this lab. Our standard ruler is going to be these beautiful grand spiral galaxies. It turns out that big galaxies, these spiral galaxies, tend to be roughly the same physical size. Now, not exactly, but as a general rule, the galaxies only show these really beautiful spiralometers when they're of a certain size. And so that can kind of act like a standard ruler for us. That size in particular is, from one end to the other, is approximately 72,000 light years. Okay, which we're going to, for the purposes of this lab, we're going to be talking kiloparsecs. 1 parsec is roughly 3 light years. So it's just another unit of distance. So a kiloparsec is 1,000 parsecs. So in those units, kiloparsecs, which we use when we're talking about very far away things, the size of this spiral galaxy would be 22 kiloparsecs. And again, most spiral galaxies are about that size. So if we see a spiral galaxy in our sky and we know how big it is in terms of its angular size, right, and we know that it's roughly 22 kiloparsecs large, we can estimate its distance, right, using the standard ruler. It's pretty cool. Now we're going to do that using the small angle equation, but we're going to modify the small angle equation to work in these units for us. So this is the small angle equation we're going to be using for this lab. The distance in kiloparsecs is going to be equal to, again, these numbers are here just because of the units that we're using of kiloparsecs and a really small angle. So the distance in kiloparsecs is equal to 1,000 times the diameter of an object in kiloparsecs divided by the angle, if that angle is measured in milliradians. Now, for our purposes here, okay, the milliradian is like a degree. Okay, it's just a really, really small degree. It's a very, very small measure of angular size. Because we're looking at faraway galaxies, they're really small in the sky, and so we're going to be measuring those in milliradians. Now, this is where this lab gets so awesome, because we're going to actually be able to do this with just like really simple tools, looking at real pictures of the universe. And I just want to show you some examples here. We're going to actually measure the distance to a galaxy a second. All right, so this is the data we're going to be using. This is a great set of galaxy images and galaxy spectra, right? And so the image is what we're going to use to determine the distance to the galaxy. So I'm going to click on this image for NGC 1357. And what's great about this is we've got a galaxy here. Okay, and there's some instructions on the screen. But what's great is I can click anywhere on this image and it's going to tell me the location of the pixel. And if I click on 2 locations, it'll tell me how many milliradians apart those 2 pixels are. So I'm going to click the greatest extent of spiral I can see here. So maybe right kind of here. Okay, and then I'm going to click on the other side right here. And maybe I went a little too far. I know what the number's supposed to be, so I'm going to go in a little closer. Okay. Alright, so I'm getting about 0.9 milliradians. 0.9 milliradians. So I'm just going to write that down a second. So what that's telling me here is that's my alpha. So we're actually going to solve this problem here, right? So if alpha is 0.9 milliradians, I should be able to figure out, right, using this standard ruler, how far away this galaxy is. So let's do that. The distance is going to equal 1,000 times my diameter, 22 kiloparsecs. Boy, it'd be a lot easier if it was exactly 1 milliradian, because then I wouldn't have to actually divide it. We'll say divided by 0.9. Okay, and we'll just do this roughly. Okay, so I got a rough calculation here. This is approximately, let's see here, 25,000 kiloparsecs. That's a really simple calculation. It's based on the assumption that that galaxy is about 22 kiloparsecs large, which is not a bad assumption. It gets us in the ballpark. And just like that, with a couple clicks of the mouse, I've measured the distance to this particular galaxy. I think it was NGC 1357 or something like that. Now, what we want to try to do next is measure the velocity, right? If we have velocity and distance, we can get a point on this Hubble law graph. Okay, so this is also very cool because I can go back now to this great list of all this data here, right? Like these real images. And now for NGC1357, instead of the image, I'm going to click on the spectra. Now this is really cool. Now we've learned before about the Doppler shift, right? And you saw a little bit in the video that as something's moving toward or away from us, the wavelengths of light actually shift. And that's telling us about the speed with which it's moving toward or away from us. Now what we have here are two different spectrum. I want to look at the one on the right first. So hydrogen gas has a really bright emission line called hydrogen alpha. It's in the red. And you can see down below here that H alpha, this red emission line, is typically located near 6550 angstroms. Now angstroms is a different unit of measure than we're used to probably, but it's just an extra digit on nanometers. So this is about 656 nanometers. That's where it's located if you're at rest, like if you have hydrogen gas glowing in the lab. But this is a real spectra of this galaxy, and it's showing that the hydrogen alpha lines, these bright emission lines, are actually shifted over several angstroms. So what's cool about this is I can click on this spectrum like at the peak of this, and it will tell me at the bottom how many angstroms that measured point is. So anywhere I click, it'll tell me how many angstroms that is. I'm going to click right at the peak of the hydrogen alpha. It says that that is at 6608 angstroms. Now I can see that at rest, it's supposed to be at about what would this be? 656, we'll say. That's pretty close. 656. All right, so this is cool. I'm going to write this down. So the H alpha line is supposed to have a wavelength of 6560, we'll say, angstroms. That's roughly. Okay? Let me just check back. What did I measure? I measured that it's 6608 angstroms. Right? So this is the one I measured. 6608 angstroms. Now we haven't done much with this equation, but we can actually calculate the speed of an object by the wavelength shift using the Doppler effect. So this is what the Doppler effect equation looks like. Now you won't actually have to do this in the lab. I just want to show it to you. Okay, the shift of wavelength, this little symbol means like the change in wavelength over the wavelength when it's at rest, is equal to the velocity over the speed of light. So we can figure out what the velocity of this object is just by looking at the shift of this wavelength. So let's just do this calculation. I just want to show you that these calculations aren't difficult. Like, it's just algebra, and yet we can figure out the age of the universe. Like, it's kind of amazing. So let's figure out what's the change in wavelength here. This is 656 to 6608. Let's see, what is that? That's like 48 angstroms. Okay, so 48 angstroms is our change in wavelength, and that'll be divided by the at-rest value. That's this one. So 6560 angstroms. Okay, and again, this is just rough, but I'll just pop up my calculator here, and I've got 48 divided by 6560, and that's 0.007, we'll say here. So let's see what this means, 0.007. That means that if you take the speed of this galaxy and divide it by the speed of light, which is the fastest speed in the universe, right? It's incredibly fast speed, the speed of light, that we get this number, 0.007. So if I want to say percent-wise, this is like 0.7% of the speed of light. So I can figure out what this actually is, right? I can figure out the actual velocity if I multiply both sides by the speed of light. And so this would be like times the speed of light would give me my velocity here. So that would be, let's see, the speed of light in kilometers per second is 300,000. So I can multiply that really quick. Take this number times 300,000, and that gives me 2,195. So the speed of this galaxy is 2,195 kilometers per second. That's incredibly fast, right? It's really, really fast. So there, look at that. What we've got here is velocity. So we measured, on the previous slide, we measured that the, lowercase d, the distance is 25,000 kiloparsecs, and that the velocity is 2,195 kilometers per second. Now what that means is that with those calculations, which it seems like a lot of calculations, but I'm just doing it on this little scratch piece of paper, right? I have a velocity and I have a distance, and so that gives me a point on my graph. And honestly, with even a single point on my graph, I could, in principle, find the slope, which means I could, in principle, with that single point, I could find an estimate of the age of the universe, right? But if I did this for like 10 galaxies, then I would get a bunch of measurements, right? And I'd get a fairly accurate, or kind of like average measurement of an estimate of the age of the universe. So it's pretty powerful, yeah? Now I just want to mention one other thing, which is this velocity. Well, actually, I'll mention a couple other things. The velocity could be expressed as kilometers per second, but another way to express it is just this number, right? Because the speed of light doesn't change; it's a constant. So this number is a fine way to express distance, and what we call this number is the redshift, z. I always put a little line through my z's, but the redshift is just this ratio of velocity over the speed of light. So we'd say that this galaxy has a redshift of 0.007. Okay, this is where we're headed. All right, so in this lab, we're going to be measuring exactly this kind of stuff. Now, there's a lot of calculations I just did. Once you've done these calculations once, which I just did for you, okay, it's not really that fun to do it over again. So what we'll do is we'll use a spreadsheet to help us do these calculations. Now, there's one other little detail I have to share with you. We looked at these spectra, and in particular, I showed you the hydrogen alpha spectrum. But there are other spectra we could look at for this galaxy, other really easy to find peaks and dips. And so we want multiple measures, right? The more ways we measure this, the better our results. So in addition to using hydrogen alpha, we're also going to use these calcium absorption lines. And you can see here's calcium K and calcium H, and they have a at-rest value or a laboratory value, but then you can also see that there's a shift. Okay, so since we're going to use a spreadsheet to help us do these calculations, it's pretty easy to get a bunch more data to put in here. So we're going to use actually 3 different spectral lines to help us accurately measure the redshift to the galaxy. So there's no excuse. We'll have a very accurate velocity measurement, right? Our distance measurement, is a little. It depends on that assumption about the size of the galaxy, right? That standard ruler, but our velocity measurement will be top notch. Okay, so let's look at the spreadsheet really quick. You'll have this spreadsheet which you can download, and you'll put your name in there, and this is where our chart will grow, okay, our Hubble law graph, and we'll see that we'll actually get an average value for our Hubble constant, right? So we'll actually be able to use this to measure the age of the universe. Now check this out. This is what's really cool. You see here's NGC 1357, and here is what we got for our H alpha value, and it automatically calculated for us the redshift, 0.007. So we don't have to do the calculation. Moreover, if we just clicked on our calcium lines over on the other side, and we got the other values for these lines, we could type those in as well, calcium K and calcium H, and get another measurement of the redshift. So we get a very accurate average redshift. And the spreadsheet even calculates for us the velocity in kilometers per second. And even more beautiful than that, we can use our theta value. Look at that. I don't even have to use the small angle equation. I showed you all those equations. You're like, why'd you show me all those equations? You don't even have to use them. Yeah, you're right. You don't even have to use them. But it's good that you saw them and you saw where it comes from. It's just algebra. So you plug in the value of milliradians, which you get right from that image of the galaxy by clicking on 2 sides of the galaxy, and it gives you a distance in megaparsecs, okay, which is like millions of parsecs instead of just kiloparsecs. And it even calculates for you the Hubble constant. So we'll get an average value of the Hubble constant. So your job in this lab, you'll read through the directions, which will walk you through some of the things I just talked you through. And you're going to collect data on 10 galaxies. I think here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, and so you should collect the 3 spectral lines and the angular size, and you'll spit back out Hubble's constant. Alright, and you'll be able to reflect on what you're seeing there, answer some of the questions, do some calculations, and calculate the age of the universe based on data that you collected all yourself. Alright, that was a lot of information. Hopefully it made a lot of sense. And with that, you can get started on the lab.